Hello, dear friends. This is Dr. Pramod P. Today we are going to discuss an important topic, and that is fixed point and floating point number systems. There are basically two methods for representing real numbers in computers, and they are fixed point representation and floating point representations. And let's see what's this fixed point and floating point representations, and see the difference between them, and we will be going through some examples also. Fixed point representation means fixed number of bits are used for integer part and fractional parts. So a real number, it got integer part and fractional part. That radix point or binary point is fixed, and this type of representation is known as fixed point representation and floating point representation. And in this we have a mantissa and an exponent to represent a wider range of numbers with varying precision. So varying precision is possible with this, and we have a representation, sign representation is there, sign bit is there, then after that we have a exponent, then mantissa. So that's usually the format of floating point representation. An idea about fixed point and floating point binary number representations are shown over here. Here in the first example we have a fixed number, and we have a fixed binary point over here. And in the second example the same is rearranged. The same fixed number is rearranged towards the bottom side, like 1.110011001101 into 2 raised to 6. So the power is basically, or exponent over here is 6. Binary representation is 110 for 6, and the bandis over here is those binary combination which just comes after the binary point or radix point over here. So it will be, the mantissa will be 110011001101. So that is a mantissa part, and combining sign bit, then exponent and mantissa, we will be getting the floating point representation. The features of fixed point representation are shown over here. The position of the first feature is the position of radix point is fixed. Then due to the fixed radix point, the range of numbers that can be represented is limited. That is one of the limitation. And one more limitation is on the precision. So precision is also limited because of the lower number of bits that we can use for fractional representation, fractional part representation. Then fixed point arithmetic are faster and efficient. This is advantage basically in certain cases. For example, embedded systems and all uses fixed point representation, and in that case the memory required is usually limited. So this is very advantageous in that case. It makes the circuit faster and efficient also. And finally, we can conclude that as far as fixed point numbers are concerned, it is well suited for applications where a specific range of numbers with fixed precision is required. Here the fixed point number representation is illustrated. For unsigned fixed point numbers, we have integer part and fractional part only. And for signed fixed point numbers, a number representation, we have sign, one bit is there towards the MSB part or most significant, that is representing sign, and usually 1 for negative number and 0 for positive number, and integer part followed by fractional part. Here is an example for fixed point number representation in the case of signed numbers, and here the number is, as an example, it is minus 40.75, and it's definitely a negative number. So the sign bit is 1, and 40 means it is represented over there. 15 bits are used for representing the second part, that is integer part. So exactly 40 is equal to 101000 in binary, and we need to have 15 bits together for integer part, so we need to put zeros to have a word length of 15 for integer part towards the left side of the binary pattern of 40. Then as far as the fractional part is concerned, it is 75. 75 means binary pattern is 1 1 only, but as far as the total word length is concerned, it is 32. So we divided it as 1, 15 and 16 as an example only. So definitely we will be able to find that part is having, that is fractional part is having a word length of 16. So we have only 1 1 over there. So the remaining around exactly 14 zeros we need to put to fill that part. Now fixed point number representation using one's complement. So the number, let's for an example be minus or negative 1.75. So let's have, in the previous example we had a word length of or bit width of 32, but here as an example let the word length be 8. So how will you be proceeding with the representation? We have 1 bit for sign, then 4 bits for the integer part, and the fractional part we have 3 bits. So it is 1.75 means it is basically its binary pattern is 1.11. 1.11 is the binary pattern. So 3 bit total 3 bits for fractional part. So it will be after the fraction it will be 110. Then towards the integer part we have 4 bits. So it will be like 4 bit means we have only 1 over there. So we will put it as 0 0 0 1. Then plus 1.75 means the sign bit is 0. Then if it is minus 1.75, we need to just take the ones complement of this. So the ones complement pattern of minus 1.75, the number is, representation is 1 1 1 1 0.001. Here is an example for fixed number representation using 2's complement. So the same number minus 1.75, and what we need to do is take the 1's complement at first, then add 1 to that. So the bit pattern for the example previous example, that is minus 1.75, the corresponding 2's complement representation is 1. That first one is sign, then we have 1 1 1 0 for integer part, then for fractional part we will be having 0 1 0, but previously for 1's complement it was 0 0 1 plus 1, it becomes basically 0 1 0. So that's all about the fixed point number representations in signed and for signed numbers, 1's complement number and 2's complement number. The disadvantages of fixed number systems are listed over here. Number 1 is lower precision, and number 2 is scaling issues, especially when we are going for multiplication and division, and inflexibility and limited range compared to floating point number systems. Floating point number representation. So here the format is given. The first one is the sign bit MSB. Then we have exponent and MANDISA. An example over here is minus 37.5, and how it can be written over here, and the precision over here is the word length over here is 32 bit, and it is divided proportionally as 1 bit for sign and 8 bits for exponent and 23, the remaining 23 for MANDISA part. And let's have an example. The number in this example, the number is minus 37.5. So it can be written this way. The number is 100,101.1. So that is the representation of number 37. So it can be again rewritten as 1.001011 into 2 raised to 5. So 5 is the power over here. So for power or exponent, the exponent, the bit width for that section is 8. So but 5 means it's only 101. So towards the left part of exponent part, we will be filling that part with 0. So it will be basically 5 zeros followed by 101, the exponent. Then as far as the sign bit is concerned, it is negative minus negative 37.5, means the sign bit is 1. Then as far as this Mandisa part is concerned, when we rearranged the original number as 1 point into the 1 point, then the remaining binary bits into 2 raised to 5, those section or those binary bits which comes just after that binary point. Here exactly it is 001011. So the remaining bits, to make it 23, for making it 23 we need to put zeros towards the right side of that particular number. So that's all about floating point representation. There is a standard for representing a floating number, and here we have a IEEE 754 standard for representing floating numbers. According to IEEE 754 standard, the floating number is represented as following. Then we have 4 types over here shown: half precision, single precision, double precision, and quadruple precision. And one by one I will explain to you. The first one is having 8 bits together, and 16 bit together, and in that the number first is sign bit, and that is 1 bit, then 5 bit for exponent, then 10 bits for Mandisa, and that is half precision. Then for single precision, it's altogether 32 bits, 1 bit for sign, 8 bit for exponent, and 23 bit for Mandisa. And for double precision altogether, the number of bits is 64, 1 bit for sign, 11 bit for exponent, and 52 bits for Mandisa. For quadruple precision, we have 128 bits, 1 bit for sign MSB, then we have 15 bit for exponent, and 112, that is 112 bits for Mandisa. That's all about IEEE 754 standard for floating number representation. The main features of floating point number systems are listed over here. So the first important feature is that its position, that is radix point position, is not fixed, and it is determined by the exponent. And since the radix point is not fixed, much wider range of numbers can be represented. That is, very small number to large number representation is possible with a trade off between, or a trade off in precision. Just for an example, if we are going for a lower number of bits, the precision will be lower, and if we are going for a higher number bit representation, precision will be better. Then the most common standard is basically, as already we discussed, is IEEE 754 standard. And this floating point number arithmetic can be complex, because for improving precision and all, we are increasing the number of bits, and also we can dynamically change the floating point as per the exponent value. So it makes it all the system a little bit complex. Then we have more flexibility because of all these things. We have exponent representation and Mandisa representation. And finally, the floating point number system is preferred for numerical analysis and scientific computing, and similar areas requiring a wide range of values with varying precision. So this fixed point number system and floating point number systems are very important as far as the design of and understanding of digital systems are concerned. Hope all of you may have understood the concept behind this. Thank you all for watching this particular video. Have a very nice day.